Congratulations, we are done for now with the electric field. That's the good news. The bad news is now we have to do the magnetic field. The magnetic field. It's so confusing and it's so hard to understand. And the reason is you usually start with this. We do an historical introduction to the magnetic field with bar magnets and extremely complicated, strange things, and the magnetic field of the Earth, which is actually upside down, all these problems. So what I'm going to attempt to do is explain the magnetic field in an analogy to the electric field to where at least you might understand why it's so hard to understand. And that's pretty much the best I can come up with right now. So I'm going to say that like E, the magnetic field B is defined by forces on charges. So let's think back to the electric field. So what was the electric field? Well, we said we have a charge here, Q1. And charge creates an E field. If that E field, that charge is positive, it creates an E, and E pushes charge. Okay. So it's just this intermediary to describe the fact that this charge pushes on that charge. Charge creates an E field pushes on a charge. That was the simplest idea. So for the B field, it's almost the same thing. For the B field, we have a charge here that's moving with some velocity v. And that moving field, or that moving charge, creates a B field. So you just put the word moving in front. A moving charge creates B, and B pushes, guess what? Only a moving charge. Okay? These directions are not accurate. We'll get into the directions later. I'm just giving you the idea that this one has to be moving, that one has to be moving, and B pushes a moving charge. All right? So at a very basic level, that is the difference. This is a field, has to do with forces, has to do with charges, but things don't move. This is a field, things do move. You can say, well, when they're moving, is there still an electric field? Oh, yeah. And you can say, well, wait, what do you mean moving? What if I'm moving and it's not moving, right? So this gets very confusing. And it's okay if this has confused you, because this confused someone else by the name of Einstein. So when Einstein came up with special relativity around 1905, whatever year it was, the paper wasn't about someone on a train with a rod and they throw the rod and the rod is shorter on the person on the train than the person on the ground. He wasn't thinking about that. The title of his paper was On the Electrodynamics of Moving Bodies. He was really thinking about this, because if you think about what's happening here, if what I've said is true, then if we have a charge sitting here and I just sit here and look at it, it's creating an electric field and no magnetic field. But if I walk by it, I see that charge moving and I see a magnetic field. Then I stop and the magnetic field's gone. I just see an electric field again. But if I move, I kind of see both. So this is what got Einstein to thinking, is that the reality you observe, or the things that you observe, the things that exist, depend on your frame of reference. And that led to all the other stuff he did in special relativity. So it is a very confusing idea, and so to fully bring it all together is beyond what we would do in freshman physics. The other thing that makes this difficult is mathematical. Okay, so if we want to describe the force here, the pushes, right, we know that that force F is Q times the electric field. So if the electric field points one direction, the force will point in that same direction. That's fine. All we got to do is multiply a scalar charge times a field with a direction E. If we want to get the force here, it depends on B and V, and those are both vectors. So we can't just multiply a scalar times a vector, we have to multiply two vectors. and we have to get a vector. So the only way to multiply two vectors and get a vector is to take a cross product, V cross B. So the full force on a charge is experiencing E fields and B fields is QE plus distribute the Q, QV cross B. And cross products are inherently three-dimensional. Right? So if we have B this way and V that way, it's B cross V, and the force will be out of the plane of the board. So you'll be practicing plenty of cross products and right-hand rules as we go. But this is the mathematical reason the B field is hard, is suddenly it's not just pushing in the direction of the field, it's always pushing at right angles to the field and to the velocity. All right? So that has you really excited to learn the magnetic field, or now how difficult it is. But maybe knowing a little bit of this in advance will help. We'll see.